In this video, we are going to see how to solve an electrical network using nodal analysis. As we know, the two popular network solving techniques in electrical engineering are mesh analysis and nodal analysis. We found that the basic law used in mesh analysis is Kirchhoff voltage law, that is KVL. Here in nodal analysis, it is based on Kirchhoff current law, that is KCL. In this method, we can obtain all node voltages in a network. Using these node voltages, it is possible to determine the value of current and voltage related to different circuit elements. We can find current through all passive elements. We can find the voltage drop across all passive elements. As I mentioned earlier, nodal analysis is based on Kirchhoff current law, that is KCL. What is KCL? It states that algebraic sum of current meeting at a junction or node is zero. So what is node? In general, node is a junction or meeting point of two or more circuit elements. Here, it is to be noted in this analysis that we can take node as meeting point of more than two circuit elements. The interconnection of two circuit elements, that is node. But in nodal analysis, we are preferably choosing this method. That is, the node can be taken as meeting point of more than two circuit elements. This point is very important in nodal analysis. We know in mesh analysis, the first step was identification of meshes. Similar to that, in nodal analysis, first and most important step is identification of nodes. After identifying meshes in mesh analysis, what was the next step? The next step in mesh analysis after identifying meshes was assumption of mesh current or loop current. That is, we need to identify or assume the direction of loop current in each meshes. After that, when we are taking a mesh, a particular mesh, say mesh 1, then that mesh current, say I1, will be treated as positive. If one branch is there which is common to mesh 1 and mesh 2, mesh 2 current direction is decided based on what? Mesh 1 current. If mesh 1 current and mesh 2 currents are flowing through an element which is common to mesh 1 and mesh 2 in the same direction, then I2, say mesh 2 current, is taken as positive. If mesh 2 current is opposite to mesh 1 current through the elements which is common to mesh 1 and mesh 2, then mesh 2 current is taken as negative. That was the step which we followed in mesh analysis. Similar way in nodal analysis, after identifying nodes, when we are applying KCL, we will assume that the particular node under consideration, say node 1, is having higher potential compared to all other nodes. When we are considering node 2, that node voltage, say V2, is assumed to be higher potential compared to all other nodes. Likewise, we will proceed for all nodes. That is, in nodal analysis, after identifying nodes, when we are applying KCL at a particular node, we will assume that that particular node under consideration is having higher node voltage. The potential at that node is higher compared to all other node voltages. We are familiar with this concept. The current is always flows from higher potential to lower potential. Since the node under consideration is having higher potential compared to all other nodes, the branches which is incidence to that node, the node under consideration, the current through that branches will always flow out from this node. It is leaving from this node. As we know, the current which is leaving from a node is always taken as positive current, and current entering towards a node is taken as negative current. Based on this concept, all currents are leaving from this node, so these currents are taken as positive currents. Let's see all these things in detail. Now let's see the steps to be followed in order to solve a given electrical network using nodal analysis. The first and most important point is identification of nodes. Then we need to choose one reference node. Usually it's voltage is taken as 0. Reference node voltage is taken as 0. Suppose we can have n nodes. N is number of nodes. Then one node is to be taken as reference node. So by means of nodal analysis, we need to identify n minus 1 node voltages. So we need to find out n minus 1 node voltages by means of nodal analysis. So the first step is identification of nodes. How many nodes are there? N nodes are there. And among these, we need to select one reference node. So totally, we need to identify n minus 1 node voltages using this nodal analysis. Here we need to identify all node voltages, that is n minus 1 node voltages with respect to reference node. Usually we are selecting a node having more elements connected as reference node. It is not compulsory to choose in that manner. You can choose any node as reference node. But usually it is preferable that the node having more elements are connected or the last node is taken as the reference node. You can choose anyone. Then next step is select a particular node, say node 1. We are going to select node 1, and as I mentioned earlier, we need to assume its node voltage. The node voltage under consideration is node 1 voltage is higher compared to node 2 voltage, node 3 voltage, etc. up to n minus 1 node voltages. Then based on that assumption, we can say that all currents are leaving from this node. Which node? Node 1. So if we can have a node, say node 1, say its potential is node 1 potential is say V1. So based on this concept, since V1 is greater compared to node 2 voltage, which is greater compared to node 3 voltage, which is greater compared to node n minus 1 voltage, etc. Say this node is connected to 3 branches like this. So based on this concept, we can say that all currents are leaving from this node. Say this is I1, this is I2, and this is I3. Current direction is known to us. We can apply what? KCL. Apply KCL at this node. When we are applying KCL at this node, I1 plus I2 plus I3 is equal to 0. We know current leaving from a junction is taken as positive current. Current coming towards a node is taken as negative current. Since here, based on this assumption, all currents are leaving from this node, so their sign is positive. So this is the equation which we can obtain for any node after applying KCL at that particular node. We can have n minus 1 nodes. For that n minus 1 nodes, we need to apply what? KCL. After applying KCL at each and every nodes, you can obtain simultaneous equation in terms of n minus 1 node voltages. In terms of V1, V2, V3, etc., Vn minus 1, you can obtain simultaneous equation if we are completing step 2, if we are repeating step 2 for all other nodes. Now, we can have n minus 1 unknown variables. Reference node voltage is already taken as 0. So we can have how many unknowns? We can have n minus 1 unknown. So n minus 1 unknowns we can easily solve by means of n minus 1 equations. So next step is, that is fourth step is solve simultaneous equation which is in terms of n minus 1 node voltages using suitable methods. We already learned about how to use matrix representation method for solving simultaneous equation. So you can use that one. That is very easy method. Once we know these node voltages, we can easily find out what the branch current I1, I2, I3, I4, etc. depending on number of branches. So these are the steps to be followed in nodal analysis in order to solve a given electrical network. Before solving a given electrical network by means of nodal analysis, first of all, let's see some branches in a given electrical network. How to find out branch current if the branch constituted by means of resistor or passive elements and voltage sources. For that, let's consider this question. Here the question is, obtain the expression for current marked in branches as shown below. So here the branch ends are A and B. These are the branch Hence, here we need to identify what is the value of current which is flowing through this resistor. So, the potential across this resistor, say this point is X. So, what is the potential difference across R, which is nothing but VAX. What is VAX? VA minus VX. So, this potential difference determine the value of current flowing through this resistor. So, in this case, first case, say this is your first case, this VB, see this potential is VB is 0 volt. So what is the potential at this point? It is somewhat similar to this part. So this part is ground, so this is like this. So we need to find out the potential at this point. So this is grounded, so what is this potential? This is 20 volt. Okay, so Vx is nothing but 20 volt. So this potential Vx is 20 volt. So we can easily find out current. So current is the potential across this resistor, that is VAX, VA minus VX divided by R. Vx is obtained as plus 20. So substituting that one, we can obtain the expression for current as VA minus 20 divided by R. Next question is somewhat similar to this one, but this point B is not grounded. So we can assume the potential at this point as VB, the potential at this point as VA. Similar to earlier case, say this is X, the point is denoted by X. So what is the potential of X? Let's denote it by Vx. So now let's redraw the circuit up to X. So this is your X. So this is 20 volt. This point is at VB. So how to determine this voltage? This point is at potential VB and this voltage is 20 volt. So what is the potential up to X? It is the sum of VB plus 20. So Vx is equal to VB plus 20. Now we can find out current as the potential difference, that is VAX, that is VA minus Vx divided by this resistor R. We can substitute Vx as VB plus 20 like this. So this is the expression for current under this case. So this is the second case, and third case is this one. In third case, same thing, but the polarity of this voltage source is just reverse. If you are drawing the equivalent circuit somewhat like this, this is the case. Here minus 20 is coming and this point is already grounded. So VB, say VB is 0. So what is the point, what is the potential at this point, which is equal to VB minus 20, which is nothing but Vx is equal to minus 20 volt. So what is this potential? VAX, say this point is X. What is VAX? VAX is equal to VA minus Vx. What is Vx? Vx is obtained as minus 20. So that is substituted over here, which is equal to VA minus 20 plus 20 will come divided by R. Similarly, the fourth case, here VB is there, here minus 20 is there. What is this point potential Vx? Which is equal to VB minus 20 volt. If you are substituting Vx value as VB minus 20, that potential difference, that is VA minus Vx divided by R, determine the value of current. So in nodal analysis, this type of situation will come, always will come. So if you know this concept, it is easier to write KCL equation and you can easily solve the network using nodal analysis by writing KCL at each and every nodes. So in KCL, it is to be noted that you are finding out the current through each elements. If you know this concept, you can easily write down the expression for currents. If you are able to do that one, then it is very easy to solve a given electrical network using nodal analysis. Now let's see a simple problem in order to solve an electrical network using nodal analysis. So the first problem is calculate the current through 2 ohm resistor of the network shown below. So as I mentioned earlier, the first step in order to solve a given electrical network using nodal analysis is identification of nodes. Here we need to identify number of nodes. So nodes we need to take as the junction where more than 2 elements are made. So here also node will come. So here one voltage source and resistor is meeting. So this is also one node. But in nodal analysis, we are taking node as junction where more than two elements are meeting. So this is first node, this is second node, this is third node. Then after identifying nodes, we need to take any one of the node as the reference node. Here we are taking the reference node as the third node. Since it is reference node, that voltage is taken as 0 volt. So node 3 voltage is 0, V3 is 0. So what is node 1 voltage? It can be represented by V1, V2, this is node 2 voltage, and this is node 3 voltage. Since it is reference, its voltage is 0 volt. So how many unknowns are there? N minus 1 unknowns will be there. So that is 2 unknowns. What are the unknowns? V1 we need to identify, and V2 we need to identify by solving the network using nodal analysis. So in order to solve two variables, we need two simultaneous equation, which is in terms of V1 and V2. In order to obtain two simultaneous equation, we will firstly select node 1 and apply KCL over there. We can obtain one nodal equation. And similarly, after that, we will apply KCL at node 2. You can obtain second nodal equation. These two nodal equation we can solve by means of matrix method. You can easily obtain V1 and V2. Once we got V1 and V2, you can easily find out currents through each and every branches. Let's see that one. So we selected the node 3 as the reference node. Now what we are going to do is we are taking node 1 and mark all currents which are leaving from these nodes based on the assumption that this is node 1. The potential of node 1 is greater compared to all other nodes. So this is V2. So V1 is greater than V2 when we are considering node 1. When we are considering node 1, V1 is greater than V2. When we are considering node 2, V2 is taken as greater potential compared to V1, and so on. So since V1 is assumed to be greater compared to V2, all currents are leaving from this node. Since leaving currents are taken as positive currents, when we are applying KCL, their sign is positive. So applying KCL, I1 plus I2 plus I3 is equal to 0. So this is the KCL equation when we are applying KCL at node 1. So in order to find out I1, we need the potential across this resistor. Say this point is X, as I mentioned earlier. So what is Vx? Vx is 20 volt. Why? Because this point is at the ground. V3 is 0. Its potential is 0. So what is Vx? Vx is plus 20. So what is the potential difference across this resistor? V1 minus Vx. V1 minus 20 will come. V1 minus 20 divided by the resistance value is 1 plus what is I2? I2 is, here the potential is V1, here the potential is V2. What is the potential difference? V1 minus V2. V1 is always higher when we are considering node 1. So V1 minus V2 divided by the resistance value, that is 0.5, plus what is I3? This point is at 0 volt. So V1, what is the potential across 1 ohm? V1 itself. V1 divided by 1 will. I3 is V1 divided by 1. So which is equal to 0. Now we can simplify this equation. We can take the quotient of V1 and V2 in one side and constant in another side. So what is the quotient of V1? V1 into 1 by 1. 1 will come here. Here 1 by 0.5 will come. That is 2. Here 1 will come. So 4 V1 will come. Then what is the quotient of V2? It is minus. Here 2 is coming. So minus 2 V2. And here minus 20 is coming. If this minus 20 is going that side, so it becomes 20. So the expression, final expression is 4V1 minus 2V2 is equal to 20. Let it be equation number 1. Here there is no need of equation number 1. So this is your first equation, first simultaneous equation. 4V1 minus 2V2 is equal to 20. Next we can take which node? Node 2. Here node 2 voltage is V2. Since we are considering node 2 voltage V2 is greater than V1. This is node 1 voltage V1. Since we are considering node 2, its potential is always considered as higher compared to V1. So all currents are leaving from this node. Say this is I4, this is I5 and this is I6. What is the relation between I2 and I4? I4 is equal to minus I2 or I2 is equal to minus I4. So when we are applying KCL at this node 2, the KCL equation become I4 plus I5 plus I6 is equal to 0. What is I4? I4 is equal to potential difference across 0.5 ohm divided by 0.5 ohm. What is the potential across 0.5 ohm? Since V2 is greater compared to V1, the potential difference is V2 minus V1. So I4 is equal to V2 minus V1 divided by its resistance 0.5. And what is I5? We are already familiar with this one. I5 is equal to this point potential we need to identify. This is at ground. So V3 is equal to 0. So this potential is say Vx, which is equal to 20 volt. So this potential is V2. We are assuming that V2 is at higher potential. So the potential difference is V2 minus 20 volt, that divided by the resistance value is 1, and I6 is very easy. This point is at 0 potential, this point is at a higher potential V2. So the potential across the 2 ohm resistor is V2 itself. So V2 divided by resistance value 2 gives the current I6, that is equal to 0. What is the coefficient of V1? What is the coefficient of V2? What is the constant? Let's see. So what is the coefficient of V1? Minus 1 by 0.5, that is minus 2. And what is the coefficient of V2? The coefficient of V2 is here 2 is coming, 1 by 0.5 is coming, here 1 is coming, here 1 by 2 is coming, 0.5. So what is the coefficient? 2 plus 1 plus 0.5, that is 3.5 V2 will. And here now constant is there, here constant is there, minus 20 by 1. So when this minus 20 is moving that side, become 20. So this is your equation number. Now next step is, that is step 3 is write equation 1 and 2 in matrix form, matrix representation method. So the coefficients of V1 and V2 can be write down as coefficient matrix. Coefficient of V1 is 4 and coefficient of V2 is minus 2. In the case of equation number 2, the coefficient of V1 is minus 2, coefficient of V2 is 3.5. So this is coefficient matrix. Then this is a V1 and V2 node voltage matrix, which is equal to, so what is the constant value for equation number 1? 20. In both cases 20 will. These two things are 20. So what is the next step? We need to solve V1 and V2. How to solve V1 and V2? You can use this method, delta 1 by delta. What is this delta? Delta is the determinant of this matrix, that is determinant of 4 minus 2 minus 2 3.5, that gives delta. So in order to find out V1, we need to remove the coefficients of V1, that is 4 and minus 2 in both equations. That is first column entries we are fully removing and replacing it with this one. So this is 20, this is also 20, and we are maintaining other column entries minus 2, 3.5. That determinants gives delta 1. Similarly, the first column entry is retained 4 minus 2, and the second column entry, that is the coefficient of V2 in both equation, that is get replaced with this 20 and 20. That determinants gives delta 2. Here delta can be obtained as 4 into 3.5 minus 4. After solving this one, you can obtain delta as 10, and delta 1 is obtained as 110 and delta 2 is obtained as 120. Substituting over here, what is V1? 110 divided by 10, that is 11 volt, and delta 2 is obtained as 120. Delta is 10, so V2 is obtained as 12 volt. So V1 is obtained as 11 volt. V2 is obtained as 12 volt. Now how to find out current through this 2 ohm resistor? So which is nothing but I6. What is I6? What is the expression for I6? V2 divided by I6 is V2 divided by 2. What is V2 we got? V2 is obtained as 12. 12 by 2 is 6 ampere. So in this way you can find out any branch current using nodal analysis. So next problem is find loop current marked in the network shown below. Here we need to find out loop currents IL1, IL2 and IL3. This you can also solve by means of mesh analysis. Let's see how to solve this one by means of nodal analysis. So what is the step 1? Mark nodes and identify reference node. How many nodes are there? Meeting point of more than 2 elements. So this is node 1, This is node 2. Since all the potentials are same, all these points potentials are same, we can take this as node 3. So this is node 3 that is mentioned over here. So this is your first node, second node and third node, and we need to assume one reference node. We need to select one reference node. Here we can take node 3 as reference node. Its potential is assumed to be 0 volt. Reference node potential is taken as 0 volt. Now what is the next step? Take node 1 and apply KCL. Write down simultaneous equation in terms of unknown variables. How many unknown variables are there? Since n is 3, one node is taken as reference node. How many unknowns will be there? N minus 1 unknown voltage will be there. So we need to develop n minus 1 equations. So let's see that one. So take node 1 and mark all currents are outgoing. All currents are outgoing like this. Why? Because the node under consideration, that potential is assumed to be higher compared to the node 2. So this is node 2. Its potential is V2. So V1 is assumed to be greater than V2. So due to this assumption, all currents are assumed to be leaving from this node. So when we are applying KCL at this node, the expression for current is I1 plus I2 plus I3 is equal to 0. Very simple. So what is I1? Since this point is at 0 potential, V3 is equal to 0. What is the current I1? Potential across 2 ohm resistor is V1 itself. So V1 divided by 2 gives I1. The expression for I2 is V1 minus 25 divided by 5. And what is I3? I3 is V1 minus the potential across 10 ohm resistor is V1 minus V2. The resistance value is 10 ohm. So this is equal to 0. Now we can separate the coefficients of V1. What is the coefficient of V1? V1 into 1 by 2 will come here. Here 1 by 5 will come. Here 1 by 10 will come. And what is the coefficient of V2? Now we can take it as minus V2. What is the coefficient of V2? Only 1 by 10 is coming. That is minus 1 by 10 V2. Which is equal to, what is the constant term available here? Minus 25 by 5. Minus 20 by 5 is 5 itself. So minus 5 when we are going that side become 5. So this is your equation number 1. So this equation can be simplified as, this is 0.8 V1. Please verify this one. 0.8 V1 minus 0.1 V2 is equal to 5. Let this be equation number 1. Now we can take node 2. Take node 2, mark all currents are outgoing from this node. Why? Because under this case we are assuming that V2 is greater than V1. So this is node 2. This is node 1. Node 1 voltage is V1. When we are applying KCL at node 2, all currents are outgoing. So I4 plus I5 plus I6 is equal to 0. What is the expression for I4? V2 is greater compared to V1. The potential across 10 ohm resistor under this case is V2 minus V1 divided by 10 ohm. What is I5? This point is at 0 potential. V3 is 0. So the potential across 4 ohm resistor is V2 itself. So I5 is V2 divided by 4 and I6 is V2 minus 50 will come. So V2 plus 50 divided by the resistance value is 2, which is equal to 0. Now we can separate the coefficients of V1. V1 coefficient is coming as minus 0.1 V1 and V2 coefficient is coming as, here 1 by 10 will come, that is 0.1. Here 1 by 4 is coming. Here 1 by 2 is coming. After solving, you can obtain 0.85 V2, which is equal to, so here plus 50 by 2, that is 25 is coming. When this 25 is going that side, it will become minus 20. So this is your equation number 2. Now we can represent equation number 1 and 2 in matrix form. So in matrix form, we can write in this manner. What are the variables? V1 and V2. We need to find out the value of V1 and V2. Then what is the output? That is constants 5 and minus 25. So this is 5 and minus 25. What is the coefficient of V1 in first equation? 0.8, and for V2 it is minus 0.1. Here minus 0.1 in second equation. Here it is 0.85. Okay, this is the matrix representation of equation number 1 and 2. Then we need to find out V1 and V2. V1 and V2 can be find out by means of delta 1 and delta 2. So what is delta? Delta is equal to 0.8 into 0.85 minus 0.01 will come. The value is obtained as 0.67. And what is delta 1? Delta 1 value is obtained as 1.75 and delta 2 value is obtained as minus 19.5. Now we can substitute delta 1 and delta 2 in these two equations. What is delta 1? It is 1.75 and delta value is 0.67. Solving this one, we can obtain V1 as 2.61 volt. So this potential V1 is obtained as 2.61 volt. And the V2, which is equal to delta 2 divided by delta 2 is minus 19.5. What is delta? 0.67. After solving this one, we can obtain the value as minus 29.1 volt approximately. So this potential V2 potential is minus 29.1 volt. Now what we need to find out this loop current. This loop current we need to find out. In this case, first case, we assume that our current I1 is nothing but current is flowing through 2 ohm resistor. But loop current 1 is opposite to that one. So IL1 is nothing but minus I1. Okay, what is I1? We already found the expression. I1 is V1 by 2. So IL1 is equal to minus I1, that is minus V1 by 2. So IL1 is equal to minus V1 by 2, which is equal to minus 2.61 divided by 2. How much is coming? It is coming as minus 1.31 volt. Okay. Similarly, IL2. In order to find out IL2, this is IL2. It is the current flowing through 10 ohm resistor. In first node, we assume that I3 is the current flowing through 10 ohm resistor. That is nothing but IL2. So IL2 is actually I3. This one. So what is I3? V1 minus V2 divided by the resistance value was 10. Substituting, V1 is 2.61, V2 is minus 29, so minus it will come 29.1 divided by 10. After solving this one, you can obtain the answer as 3.17 ampere. So this unit is not volt, this is current ampere. So next one is IL3, loop current 3. It is nothing but current through 2 ohm resistor. For that, let's consider node 2 equation. In node 2 equation, the current through 2 ohm resistor is I6. So IL6 is equal to I6. How to find out I6? The expression was V2 plus 50 divided by 2. V2 plus 50 divided by 2, which is equal to V2 value is minus 29.1 plus 50 divided by 2. After solving this one, you can obtain the answer as 10.45 ampere. Now we can copy this one for representing all these things. We just copied the above circuit. Here IL1 was there. So this is IL1. This is IL2. This is IL3. So IL3 is obtained as this current. This current is nothing but 10.45 ampere. So the direction which we assumed is exactly same. It is coming as positive. And IL2 is this current. So this current is also flowing from node 1 to 2 because it is coming as 3.17 positive current. But the first current IL1 is coming as minus 1.3 ampere. When we are assuming this direction, its current can be represented by minus 1.31 ampere. So it indicates that our assumed direction is opposite to the actual direction. Actual direction is in this manner. In this direction, its value is 1.31 ampere. So this is the solution to this problem which we got from nodal analysis. Likewise, you can solve any network using nodal analysis. This is the homework problem. Here the question is calculate current through 5 ohm resistor using nodal analysis. Here this current source value is 8 ampere. Now let's see another problem in order to solve node voltages. Here the question is obtain node voltages V1 and V2 using nodal analysis. So in order to solve this one, first of all we need to identify number of nodes, N. What is N? Number of nodes. Node is interconnection of more than 2 circuit elements. This is node 1, this is node 2 and this is node 3. How many nodes are there? 3 nodes are there. Among this, we need to take one reference node. So reference node is taken as third node. So in that node, V3 is 0. Node 3 voltage is assumed to be 0 volt. Now, next step is we need to take node 1. We need to take node 1 and we are assuming that V1 is node 1 voltage is greater than V2. So this is node 2. So this potential is 0, V3 is 0. And as we are assuming V1 is greater than V2, all currents are leaving from this node. Say this is I1, this is I2, and this is I3. After applying KCL at node 1, the equation become I1 plus I2 plus I3 is equal to 0. Why? Because all living currents are assumed to be positive current. So what is I1? I1 is opposite to this current source. So it is minus 1. I2 is V1 divided by 2. V1 by 2. And I3 is V1 minus V2 divided by 2. V1 minus V2 divided by 2, which is equal to 0. Now we can separate the quotient of V1, V2 and constant terms. So V1 quotient is coming as, this is 0.5, this is also 0.5, 1 will come. So the quotient of V1 is 1. And the quotient of V2 is coming as, here minus 0.5 will come. So it is minus 0.5 V2, which is equal to this one. So this is your equation number 1 when we are applying KCL at node 1. Now we can choose second node. So this is your node 2 and this is your node 3. Here node 3 potential is assumed to be 0. Why? Because it is taken as reference node. Now in this case, when we are writing KCL at node 2, the node voltage V2 is assumed to be greater than V1. So all currents are leaving from this node. Say this is I4, this is I5 and this is I6. So at node 2, KCL equation become I4 plus I5 plus I6 is equal to 0. What is I4? I4 is V2 minus V1 divided by 2. What is I5? V2 by 1. And what is I6? It is opposite to this current source. So it is minus 2, which is equal to 0. Now similar to earlier case, we can separate the quotient of V1 and V2. What is the quotient of V1? It is coming as minus 0.5. And what is the quotient of V2? Here 1 by 2, that is 0.5 is coming. Here 1 is coming. So its quotient is 1.5 V2 and here 2 will come. So this is your equation number 2. Now we can represent equation 1 and 2 in matrix form. The variables are V1 and V2. What are the quotients of V1 in first equation? It is 1. In second equation, the quotient of V1 is minus 0.5. In second equation, the quotient of V2 is 1.5. The quotient of V2 in first equation is minus 0.5, which is equal to the constant in first equation is 1. In second equation, it is 2. Now, how to find out V1? V1 is equal to delta 1 by delta and V2 is equal to delta 2 by delta. And we know delta is the determinant of this matrix. Delta 1 is the first column is replaced with this one and second column is replaced with this one, that obtained as delta. Determinant of that matrices gives delta 1 and delta 2. So the solution is left to you. The final answer for V1 is obtained as 2 volt and final answer for V2 is obtained as 2 volt. So please complete this problem.